Good morning, students. Today's topic is managing variation, statistical process control. Now let us understand the concept of software metrics collection process. I hope everyone are observing the diagram on the screen where the software metrics collection process is explained with the help of the diagram. The first phase is data collection, where the data is collected from software product, software project, software engineering process. Depending upon the measures considered in the data collection, the computation of metrics is calculated. Depending upon those metrics, the metrics are evaluated with the help of set of indicators that we have already discussed in the previous sessions. The software process and the product it produces both are influenced by several parameters. Example, the skill level of practitioners. Here practitioners are nothing but the software professionals. The other parameter is structure of the software team, and the next parameter is knowledge of the customers, and the next parameter is the technology that is to be implemented in order to process the software, the tools to be used in the development activity is another parameter. Depending upon these parameters, metrics are collected for one project or product, which will not be the same as similar metrics collected for another project. Hence, there is often significant variability in the metrics that we have collected as a part of the software process. There are two different types of control charts that are used in the assessment of metrics data. Those are the moving range control chart and the individual control chart. Before going into the types of the control charts, first of all let us know how can we tell if improved or degraded metric values that occur as consequence of improvement activities are having a quantitative impact. The other query is how do we know whether we are looking at a statistically valid trend or whether the trend is simply as a result of statistical noise. When are the changes either positive or negative to a particular software metric meaningful? These are all different queries that will be raised whenever we are developing a software project. A graphical technique is available in order to determine whether changes and variations in metrics of data are meaningful. This is called control chart. It is developed by Walter Shewhart in the 1920s. This technique enables individuals interested in software process improvement to determine whether the dispersion it represents variability and location, moving average of process metrics, which are stable or unstable. Stable is referred to the process that exhibits only natural and controlled changes, whereas unstable identifies the process which exhibits out of control changes and the metrics cannot be used to predict the performance. It means the process which shows only natural or controlled modifications is represented as stable process metrics, whereas the process which shows out of control changes and those changes cannot be predicted by its performance is represented as unstable. Now let us understand how can we be sure that the metrics which we collect are statistically valid. If you observe the screen with the help of the diagram, it is explained clearly. The metric data for errors uncovered per review are. On x-axis on the diagram, the values represent projects, and on y-axis the values represents errors found or review R. It is represented as ER. Consider a software organization that collects the process metrics, errors which are uncovered in the reviews. The review depends upon the hour. It is represented as ER. ER is the errors that are uncovered per review hour. Over the past 15 months, the organization has collected these errors for 20 small projects in the same general software development domain. The resultant values for these errors are represented in the figure. ER varies from a low value of 1.2 for project 3 to a high value of the value represented 5.9 for project 17. In order to improve the effectiveness of reviews, the software organization provided training and mentoring to all project team members beginning with the project. It means the reviews are to be improved in order to achieve the effectiveness of the organization product, and hence the organization provides training and also mentoring team members in order to have an idea of the project. An overview of the procedure required to develop a moving range control chart for determining the stability of the process is provided with the help of the following steps. If you observe the diagram with the steps, you can easily identify as how to develop a moving range control chart in order to calculate the stability of the process. The first one is calculate the moving ranges. We need to calculate the moving range value, the absolute value of the successive differences between each pair of data points. Then plot these moving ranges on your chart. If you observe in the diagram, on x-axis the project values are considered, and on y-axis difference in successive ER values is plotted. Coming to the next point, that is calculate the mean of the moving ranges. We need to calculate the mean value of these moving ranges and plot it as MR bar, that is shown in the diagram as the center line on your chart. And the next point is multiply the mean by 3.268, for which the organization has calculated the average value of the process metrics. Plot this line as the upper control limit. It is represented as UCL. In this example, we have considered the software organization with 15 projects. So the UCL is given as 5.57 which is not shown. This line is 3 standard deviations above the mean. If you observe the dotted lines above the 3 lines, we are considering the UCL value. Those are 3 standard deviations. The deviations occur depending upon the type of projects we take. Using the data represented in the figure and the steps suggested by Geltner, we provide an MR control chart. The MR bar represents mean value for moving range data, which is considered here as 1.71. The upper control limit is 5.58. In order to determine whether the process matrix dispersion is stable, a simple question is asked: are all the moving range values inside the UCL? For example, noted, the answer is yes. Hence, all the matrix dispersion is stable in the considered example. The individual control chart is developed in the following manner. The first one is plot individual metric values. We need to create an individual control chart, then we should first plot the individual metric values. The next step is compute the average value. It is represented by AM for the metric values. And the next step is multiply the mean of the MR values. MR values represented by MR bar with the constant value 2.660, and then add average value for the metric values computed in the step 2. This results in the upper natural process limit represented by UNPL. Then plot it. Coming to the next step, multiply the mean of the MR values by 2.660 and subtract this amount from AM. AM is represented for average values for metric value computed in the step 2. This results in the lower natural process limit. It is represented by LNPL. Plot it. If the LNPL is less than 0.0, it need not be plotted unless the metric being evaluated which takes on values that are less than 0.0. If specified in any metric, then we'll be considering that value. The next step is compute a standard deviation as UNPL multiplied with average value AM for the metric values divided by 3. Plot lines 1 and 2, standard deviations above and below AM. If any of the standard deviation lines is less than 0.0, it need not be plotted unless the metric being evaluated on values that are less than 0.0. If we can't tell signals from noise, how will we ever know if changes to the process are improvement or illusions? Said by Richard Jultner. We need to understand the signals that represent from the noise. If the changes to the process are illusions, then we cannot predict it. If it is for improvement, then we can assess it through our prediction. If any of the following conditions is true, the matrix data indicate a process that is out of control. So we'll be discussing several points when the process is out of control. A single metric value lies outside the UNPL. The second validation for metric data is 2 out of 3 successive metric values lie more than 2 standard deviations away from average value for the metrics. The next one is 4 out of 5 successive metrics values lie more than 1 standard deviation away from AM. The next step is 8 consecutive metric values lie on one side of AM. Since all of these conditions fail for the values, the metrics data are derived from a stable process and are very much fond of the information that can be inferred from the metrics data collected. Referring to the figure, it can be seen that the variability of ER decreases after project 10, that is, after an effort to the improvement of the effectiveness of reviews. In project 10, from the diagram you can observe it. It is decreased to the MR bar from above the line of the metric data. By computing the mean value for the first 10 and last 10 projects, it can be shown that the mean value of ER for projects 11 to 20 shows a 29% improvement over ER for projects 1 to 10. The standard deviation formula is represented there, sigma equal to square root of summation of xi minus mu whole square by n, where sigma represents population standard deviation, in this case the project standard deviation, and n is the size of the projects considered, and xi is each value from the project considered related to the process steps. Mu represents the mean value of the project. Since the control chart indicates that the process is stable, it appears that efforts to improve review effectiveness are working. Hence, Jultner reviews 4 criteria called zone rules that may be used to evaluate whether the changes represented by the metric indicate a process that is in control or out of control. If you observe in this diagram, there is the variation of the graph between moving range control chart and individual control chart. I hope you identified both the diagrams where the projects are represented on x-axis and the error values are represented on y-axis. If we consider moving range control chart, the error values are difference in successive values of those errors. The UCL value is calculated to be 5.57 and the MR bar is represented with the horizontal line in the graph. And coming to the individual control chart, y-axis identifies the errors per review hour and the standard deviation is calculated with the average mean values represented by AM and -1 sigma represents standard deviation with negative values and +1 sigma represents the positive values for standard deviation. and the two sigma lines are not shown in the diagram, but there exists the change in values of standard deviation as per the formula that we have observed in the previous slide. Likewise, we'll be calculating the project matrix data depending upon the range values of control chart as well as individual values of the control chart. Thank you one and all. If you have any queries, now let us discuss. Thank you one and all.